Welcome. This is a session talk on exploring microservice integration risks. And my name is Rob Sabourin. I've been involved in software engineering since probably the late 1970s, early 1980s, and all the way through to today. I've been involved in many different architectures and technologies, client server, fat client, mainframe, distributed multi-tier web, service-oriented architectures, API definitions, and more recently, REST API architectures. And um, my work and my involvement has been mostly involved in the software engineering side of it, where we're basically defining, designing, architecting, and testing solutions. Uh, Microservice architectures have been increasing in popularity over the last several years, although the technology has been around for quite some time. And a lot of people that I work with, among my consulting customer base and students, really enjoy developing solutions with microservices. However, they have a lot of difficulty transitioning from what they think is traditional sort of web-based multi-tier architecture testing to moving to microservice testing. And I like to point out to people that even though technologies change dramatically with time, the fundamental software testing methods, tools, and techniques don't change that dramatically. Of course, perhaps in microservice architecture, what we're being asked to test might be different from a mobile application that we're being asked to test. Microservice architectures generally are described by application program interfaces. And these APIs are things that are called, instantiated, invoked by programs so that people can create solutions. People can solve problems. Microservices are small units of functionality. Each microservice uh, does a focused type of activity. It does it very well, and it does it in a way that can apply to many, many different applications. So one microservice might show up all over the place in your application suite. And it's interesting to see how can we test microservices and what's different about them. And we'll take a look at that in this seminar. But I want you to start with the sort of premise that we are testing something. It is software, and the inherent nature of a software project has not changed. So people still have to have some sort of requirements, some sort of design, some sort of implementation. Programmers are expected to do some sort of unit testing. There's all these things that take place in microservice projects, pretty much the same way they take place in any project. There are differences though, because for sure we are testing APIs, application program interfaces. We are not testing, therefore, through a traditional application user interface where the user is the end user. In microservices, the user is often a programmer. So we are almost always obliged to use tools or some sort of programmatic technology to enable us to call and access the microservices, except for the most uh, trivial cases. Uh, you've got to basically use some sort of tools to access the microservices. And the microservice user is generally not a human being. The microservice user is a programmer. And the programmer succeeds in using microservices if they can create a solution. And this, of course, has to do with a little bit of completeness. So the microservices available to the programmer should be a complete set so that they can solve the problem. And it should be a sufficient set. It should be consistent. It should be backward compatible. So if I made an application last month and I have a new version of the API available, the old software should run on the new API. The new application might not run on the old one, but the old one certainly should run on the new API. There's all sorts of concerns, because this is a library, and the library is defined in terms of how applications control back-end applications. So this is microservice architectures. Um, One of the most popular types, and certainly not the only type, but one of the most popular types that I'm exposed to is called a REST API, a RESTful API. And this is basically describing a technology, a type of microservice architecture that has all sorts of fantastic characteristics. First thing to take note of is that an API is a standardized mechanism to control and observe a program. So we control it by asking it to do things. If you look at one of the ones that's actually published, eBay has a beautiful API that's described. And if you want to search for all the product listings for vacuum cleaners, well, the API is available for searching. And you can search for any string in any category you like. There's a well-defined API to do that. And it's basically controlling the back end, controlling the back end of eBay to provide you with the information, as if you were, I guess, an end user asking for all the products that were for sale that were vacuums. Well, maybe with the REST API, we're a program that wants to get that information. And then that program will somehow send that information to human beings or to other programs or processes to do something useful with it. APIs are generally standardized. There's not 50 ways to do everything. There's usually one very clean way to do something. And we should also, in these APIs, be able to observe things. So we want to control the operation of a system, and we want to observe the status of the system, the data in the system, what's happening to our transaction. We want to be able to query the state of objects, places, people, things, anything that's in there. So we observe and control, observe and control, observe and control. If you can observe and control something, you can actually create a solution with it. If you can just control it without observing it, then there's no way of you to put checks and balances in your software. For example, a search result may require you to say, I have a page size. I can only accept 200 entries at a time. And if there's 6,000 responses, well, they'll give it to you in chunks. So you want to sort of say, how many chunks are there? And then say, okay, give me the third chunk, then give me the fourth chunk, then give me the fifth chunk. So you need to be able to query things like, how big is the response going to be? And then let's manage that. So there's sort of queries and controls and queries, combining them. Generally, the REST API is independent of the technology that you're using to control it. So you can go through the same API, the exact same API, through a browser, a mobile device, or an embedded piece of software like a code running in your laundry machine in the Internet of Things. So all of these would use the exact same API. If you know how to do this, there's a tool called curl, which you can get, and you can actually type the API in and do commands just like you were typing in an old MS-DOS shell or a Unix shell, something like that. So there's any number of ways you can control the API, and the beautiful thing about the API is it will be the exact same API for different types of interfaces. And your mobile application may look dramatically different from your browser application, but the API is exactly the same. And now this is a beautiful, beautiful division of labor, because if we're saying, okay, let's put the GUI, the actual, the end user facing stuff in the device as close to the user as possible, and then we keep the business logic and the data through a clear API path, that means that we can create regression tests for the API, which can be used forever and for always, independent of the technology. So if you don't have for example, an Android version of your software, and you want to create an Android version, well, you've already got a web version, you're creating an Android version, that's great. You can regress the business logic with exactly the same API regression test suite as you did for the browser version. There's no need to create a different one. Now, for the front end, you certainly need a different one for each GUI or each class of GUI. But for the back end, for anything behind that API, it's going to be the same no matter what the technology that's calling it is. And this is, of course, a beautiful advantage of it. So the services, the data, it's all behind a clean and consistent, well-defined application program interface. Now, when we say REST API, REST API is usually described as implementation of representational state transfer models. And these models have some incredible benefits. For example, they have scalability. This is one of the amazing things we see today with the cloud-based technology like Azure or AWS or the Google Cloud or any similar technology. The back-end software is easily scalable if it's implemented with these REST APIs. It's actually really trivial to scale it up. You just give more capacity and it can scale up, it can scale down. You can only pay for the services you need on the back end. Highly scalable stuff. So this is a beautiful thing. If you remember doing scaling with multi-tier architectures, it was always a nightmare to try to prove and demonstrate that something was scalable. And almost every time you wanted to scale it, you spent tons of effort tweaking, adapting, and adjusting things. Well, with the REST API, the scalability is sort of a natural side effect of the architecture. There's standardized error handling. So this is nice because you don't have to have, for every single library you get, a totally new error handling mechanism. And it's cacheable, which is pretty cool. Go back to the eBay example. If you're doing one of these big searches, you don't have to go and hit the backend database every time you want to access something in that search, because they can cache it, and you'd only refresh the cache if something in the related data had changed in the interim. So it's beautiful stuff. It's a nice technology that way. What does it look like? Well, the API is accessed through the basically hypertext transport protocol, the HTTP protocol. And there's really very, very few things that we can do with the HTTP protocol. So these are used to implement all REST API implementations. So the first one would be the HTTP command GET. So GET is a command that reads information. So if you want to query something, you would usually have some sort of a URL, which is like an endpoint, and then you'd say get that endpoint, and it would return in whatever type of package you're expecting, a JSON or XML or whatever format you're supporting. You would get the information back as basically text. And the get one is to read things. There's creating information or putting information to the system. That's the post verb. So I want to create a new user. I'm going to post something. Post. Put amends things. So this is can add or change things. Delete deletes information. So if you want to delete a record, there's the HTTP delete verb. And when you combine the get, post, put, delete, you can do almost anything. The HTTP has standardized status. That's the error codes, success, failure, and if it's a failure, what type of failure, very specifically. Content types are well defined, and there's a body which is basically standardized, and that we can basically form into what you might call a payload. So a payload is like that package of information that goes back and forth between the client and the server. There's standardized status codes. These are error codes or return codes. If things fail, if they succeed, what's going on. There's many of them. They're well defined. This is a big list of them. I'm sure you've seen some in your day, like, for example, in the 400 range, bad request, 404 not found, 408 request conflict. All these are basically standardized HTTP response codes. Now, the content that's moved back and forth when you get a query or you're requesting some information, it will generally package it, and you can define what type of content to use for that. So the two popular ones these days, among at least my clients, are JSON objects and XML objects. I'm an old XML guy because that's I was brought up on XML. But today people are using JSON or XML, sort of intermixed. JSON seems to be more popular, and there's other formats as well. The basic thing is JSON is handy for the nice notation it's got, which is derived from JavaScript. And XML is also very clean for defining things. It's a tag language. It's very very clean markup language style, like HTML. So those people who prefer XML can do it. Some systems will allow you to switch between, so you can say I want JSON or I want XML, and some will choose only one or the other. It's important you know how to parse them, but you have libraries that can help you do that. The HTTP header contains some extra information. They call it metadata around the message, which says what the type of content is, the host, cookies, if there's any data that's stored in cookies, any authentication details required for handshaking, etc. To followers, well, what you would do is type in, if you wanted to do this by hand, HTTPS :// api.twitter.com, then /1.1, which is a version number, /followers, which is an endpoint, /list.json, which is where you're going to be putting the result. So it's a get. So you're going to get something, and it's going to put the result in a JSON format. And there's all sorts of parameters that are in the payload. So if you look at the parameters, the user ID is considered optional. The cursor semi-optional. This is between you and Twitter. You don't always need all these parameters. In fact, a lot of them seem to be optional. There's got to be a few mandatory ones in there. This is just the example of what a response would look like. So in this case, this is a simple JSON thing where you have username, stuff about where the cursor is. I suppose that's because they're giving you a list of data, so you want to get a pointer to it. Now, there's tons of examples of REST API available online, and there's tools that will let you look at it and edit it and manage it and work with it. There's all sorts of great stuff. So there's no question that the resources are there for people and the tools are there. And most of the tools are either open source or commercial tools have what they call a community version to let you manipulate information in your API. A tool like Postman will give you all sorts of information about your API. So you can basically see what the API is, and they're well described. People like to describe APIs. Now, I like to look at APIs and say, okay, so what can go wrong? If I'm doing testing work, yeah, I'm interested in what the format is and all that type of stuff, and I guess I'll be concerned about that. But what can go wrong? So we might have on the client side using an older version of a service, so the version of the service may be inappropriate. Maybe the syntax, we're formatting our HTTP wrong, or we're missing a mandatory parameter in the HTTP structure. We may also be invoking microservices in a sequence that might not be something that's meaningful. They might want us to, for example, start by putting in a request for a search result and give us an index for that search result, and then we manipulate through the search result. But if you didn't ask for search result, how does it know which one you're pointing to? So there's order of operation, order of calling microservices that may be applicable. Now they say that these microservices and RESTful APIs are stateless, but that doesn't mean that there's not a order of operation. And I like to say, let's test the sequencing of things. If we can run any service in any order, well, let's try. Let's see if there's any dependencies there. There's risks related to mocks. Sometimes during development, programmers will use fake versions of services because naturally the real version might be hard to access, tricky to get to, remote, distant, all this type of stuff. So what you'll do is you'll basically say, I will use a mock service, but that mock service might not match the real behavior. Now maybe it matches the packet formatting. So your payload is right, the package is right, the error codes are right, but the behavior in terms of the time response of the system might be inappropriate. It might be too slow or too fast or just very different from the real world. So I want to make sure if the development used mocks, and almost always there is some mocking used, especially for external services that are not on your local cluster that you depend on. For example, validating a credit card. And if you're using mocks, then there's a risk that in the live system the behavior is different. The real-time behavior is different from the mock object that's used in development, and also maybe the results are different too. Don't be confident that the mocks match the real world behavior. They, in fact, probably are a little bit different. Then there's what we call white box concerns. So this is risks associated with the actual code. And excuse my spelling mistake here for the word statement here. But do we during development simulate all the possible error codes? Did the developers do unit testing of that? Are they sure that they handle that in a meaningful way? Um, and then code, did we look at the code that's being created? Have we had a chance to review it? Has someone else reviewed this code? Someone who's either a domain expert or a microservice architecture expert. Code reviews are very important, especially in companies that are transitioning legacy code. They're taking legacy code and they're migrating it from a traditional client server architecture or from a multi-tier architecture to a microservice architecture. And it's not just putting an API wrapper around old code. Actually, it involves re-architecting the code so that the state is moved around in the payload, not persistent in the server. So this is very important. Otherwise, you lose the benefit of scalability of these things. So we want to look at the code, make sure we're doing that well. There may also be white box testing. Did they exercise different coverage notions, the statement coverage, path coverage, decision coverage, branch coverage? All of these things are white box issues that you can basically look at by discussing with the programmer what's changed in the code, maybe pairing with them to walk through code changes to make sure that there's nothing missing, but also to look at what software uses the code that's changed to make sure that you exercise that. Even if you don't know how to test the code, if you know what features, functions, and aspects of the microservice uses the code that's changed, you'll be able to figure out how to test that. So that's the white box notion here. We have also got non-functional attributes, security, performance, robustness. These are ones that come up a lot. And so for robustness, we can do things like fuzzing the payload, just basically try to corrupt it, or try to, I'm not saying corrupt it in the sense of corrupting a miner. I'm talking about corrupting the data, or fuzzing it or breaking it or doing mutations to it to see how robust the application is. Uh, there's non-functional tests also related to performance, too fast, too slow, the throughput. Okay, throughput would be like transactions per time. Latency would be from when you request something, how long does it take to get it started, to get doing, and too slow would just be the net transaction time, round trip from when you send the API to when you get the response back. And then there's payload related stuff where we might have risks related to the content type. So if it's XML or JSON, is it the correct form or incorrect form? That's a syntax issue. Then there's parameters, the wrong type or number or missing parameters. You may have more parameters than are supported. Is that okay? You may have less parameters. How are missing parameters treated? We saw the list from Twitter that had all these optional parameters. Are there optional parameters? What happens if the optional parameters are not there? And it's interesting to note that even if it's optional, it's still something that could influence the behavior of the system. Because if it's not there, what does the system assume it is? Does it have some sort of default value that it shows in there? And is that something that's arbitrary or is that controllable? Can you tell the system what to do with parameters that are not included? Then there's the combinations of variables, because you have so many variables in these payloads, and I've seen 50, 100, and more variables in one payload definition. looking at just eBay examples. You get lots and lots of variables in there. So you really need to test the multiple combinations of these variables. How do you choose the combinations? Do we use the Pareto set, which is the 80-20 rule, which suggests that we're going to test the most common set of values? So take the ones that happen, like the 80% of the combinations that happen 20% of the combinations that happen 80% of the time. That's 80-20 rule, Pareto. Or we might try every value for every variable at least once, or maybe take every pair and try all the combinations at least once, or some blend of combinatoric testing. Uh, it doesn't hurt once you've got a payload definition to start looking at domain analysis of variables. Can you identify values using partitioning, equivalence classes? Can you identify boundary values? Any variable with a continuous range might have a boundary condition that's interesting. There's nothing special about REST APIs that makes it immune to boundary bugs. So these are all things that are risks related to the payload. I would suggest that for payloads, you want to have payloads that exercise all the variables and all the classes and all the boundary conditions, the minimums, maximums on the edge, a little below, a little above, etc. So that's traditional domain analysis of variables that should fit there. Plus, on top of that, it's very, very important to look at your business logic. And so many of my customers are doing this with side-by-side testing, because they've given a REST API and they're saying, okay, this API is implementing exactly the same business logic as the old system, but we had to modify the code to get it into this new form. So how do you test that? They suggest side-by-side testing, where you have the old version of the software and the new version of the software, and you try all the different business rules to see if it works. Now, to find tests like that, there's certain decision table test design techniques, regression strategies. There's some interesting tactics, but that is something that we're seeing a lot of in REST API testing. People are developing new versions of software with nice, clean APIs, but they're doing a migration of the legacy code for the business logic. So I want to make sure, can I make sure with a reasonable number of tests that the business logic is still correct? And that's where we can do things like decision tables to help us find a nice set of tests to exercise the business logic. So these are the types of things, I like to say is, what can go wrong in a REST API product? There's a type of testing that fits very nicely in the universe of REST API, and it's called contract testing. Contract testing, by the way, is not new. It's been around, as far as I remember, since sometime in the 1990s. Basically, contract testing fits any system that has a defined API, and there's an agreement between the person who provides the service and the consumer of the service. So they agree on what's the API, what's the definition, what's the parameters, what's the types, what's the value ranges, what's the error codes. We agree on what's the format, what's the range, what's the constraints. We agree on that, and we will verify that before we use the service. So the client has expectations, it will check the expectations match what the service is providing. The service has expectations, it will check to make sure those are matched. And this is contract testing. Contract testing is supported by a lot of tools today. So you can get some beautiful REST API tools that will go in there and take a look at the definitions of the APIs and check to make sure that the client and the server side, or the consumer and the service provider, are in sync. We look for broken changes by the provider on endpoints or payload. So did something change in the way things are coded? Did something change in how we access it? And this is something that would be a violation of a contract. So contract testing is actually a type of, if you will, a static analysis that will look actually at the code to see, or the code and the structure of the code to see if we've got the right behavior. So the consumer is basically checking, does the provider support the agreement we made, and vice versa. So we verify the expectations of the consumer and of the provider. And tools are great at doing this. They will give you all sorts of insights into whether you are in sync. And these are great, you know, great problems to find. It should be done anytime you have a new update to your API. You should run some sort of contract testing to verify that the consumer and provider have a shared understanding of what requests and response will be needed. So contract testing, verifying that the consumer and the provider have a shared understanding of what the requests and responses will be needed. Contract testing looks at the response data, looks at the form of the XML, JSON, whatever parameters there are, make sure the data is in sync, looks at maximum lengths, data types, required fields, HTTP code returns, etc. So that's contract testing. A little bit like static analysis, right? You're looking at the non-executable stuff. You're seeing, is the code coded correctly? Now, there's also what's called behavior testing. So this is the testing where we want to, we're not just not checking, is the API okay? Contract testing is great and it's necessary, but it's far from sufficient. Business logic should be exercised. We want to confirm the business logic is correct, confirm that our processing algorithms do what they're supposed to. Does the code actually work? Does the code do what it's supposed to do? Not just what it's programmed to do. That's what, we can look at what it's programmed to do, but I'm concerned, does it do what it's required to do? And then there's solution testing. Can someone actually create an app with the API? As a tester, I like to look at this API and I like to create a test application with the API. Not the real application we're going to be selling to the consumer, but a test application to see if I can model what a user does. And I am a huge advocate of modeling around the user. I care about the user more than anything else. I want to make sure that the user can do what they need to do with the software that I'm testing. Well, if you're testing an API, your user is a programmer. So they have to be able to write programs with the API. Now, you don't have to write fancy programs with complex GUIs and all sorts of bells and whistles and fancy features. You could make a little batch program with a DOS command shell or a Unix command shell and tools like curl, which I mentioned earlier, that will just use little command line things, and they can implement any HTTP request, and it can send the request, read back the results, and you can parse the results. So you can do this with batch files, or you can do this with scripting languages. Of course, my favorite scripting language is Ruby, but if you don't know a scripting language, probably the one to learn these days is Python. And the amount of Python you need to know to control and read back HTTP requests is really quite minimal. I'm not suggesting it's trivial, but it's just a way to create scripts that can access the API and get results back. It's like making a little program with the API. So Python is what I would direct you to if you don't know a scripting language. But I'm a sort of a fan of Ruby. I think Ruby's perfect for this. If you know Ruby, it's great. If you know Perl, it's also perfect for this. But stick to a scripting language that's got team awareness, that other people on your team are familiar with, so that if you get stuck, you can just rely on some help. Putting together scripts that control microservices using a curl command or command line, things like curl, does not take a lot of time to do. I was testing this, how long does it take? There was an API that was a microservice API that was implemented in a course on programming in Java. And I took that, looked at the API, and with Ruby and curl, was able to implement between 5 and 10 lines of code for each API call. And I created a whole bunch of little scripts just to exercise the API call. And then I called the scripts in different sequences to simulate an application doing things in different orders of operation. And this took just a few minutes per API call. So I would suggest that it does solutions do involve programming. You are programming when you're using an API. APIs are for programmers. So if you love testing from the point of view of the end user, think of this. Your end user is indeed a programmer. Now, you will probably also want to test the application that they're creating. But for that case, you don't need to retest the service. You just got to make sure the application is sending and receiving the right stuff. But all of your business logic regression testing should be at the service API level. All right. So what else do we want to do? Well, I like to look at the risks that we explore. Now, there's capabilities. So we want to make sure for our services, we want to make sure that the application does what it's supposed to do. So what I like to do is I like to sort of discover and manipulate variables. Variables are things that can change, that influence the behavior of the system or are influenced by the behavior of the system. I like to observe the behavior, validate that it's correct. So select variables, select values, make sure it's correct, and look for unexpected emergent behaviors, situations that we don't expect. So this is looking at capabilities. So does the application do what it's supposed to do? Then I've got to be concerned about what I call cross-story interference or cross-story relationships. Is your application, or your API providing a service? Yes, it's providing a service. Do different APIs in different orders interfere with other APIs in different orders? For example, if you have one API which is on, let's say, something like eBay, and one API is for you to query what are the auctions, but another API is to start and stop or to cancel options. Start, stop, cancel. Start, stop, cancel. Well, what if someone cancels an auction while you're looking for something? And this is, you might think this sounds like it's a trivial thing, but it's not. With microservices, this is actually a beautiful testing situation. It will happen in a highly scaled system. You will see these interference things going on. Someone will try to cancel an operation, or someone will try to remove an object from inventory while you're doing something else with the object. This means that there is a risk of resource sharing or contention, multi-threading risks, things that are multiple objects are waiting for the same event to take place. All of these things can happen. If someone takes out an object, it invalidates the result of my previous search. Should I do the search again? How should it behave? So I want to look for these things. I want to say, if multiple stories manipulate common objects, how do they interact with each other? And that's in order, out of order, in parallel, with different people doing things on the same object at the same time. Think of this as a simple test on eBay. Have one program just looping around and making a list of all the auctions which are selling a certain item. And then have someone else adding and removing auctions in a loop, adding auctions and removing auctions that sell the same item, and see if it all syncs up. And of course, that is for me a beautiful example of cross-story interference. And if it's well coded, this will not be an issue at all. Not hard to set up. If you build little scripts, running them in different orders, looping around, not too tricky to do. Then there's the notion of testing failure modes. Failure mode testing is testing a system to see what can break. And microservices are just like any other piece of technology. There's risks that they break if you do something weird. So what can break? Invalid input. Sure, maybe invalid input could cause it to screw up. Maybe out of range values or negative values when you're expecting positive values. Things that are invalid types could cause it to break. Maybe there's risks in terms of any environmental factors that are needed. For example, how much memory, disk space, network bandwidth, CPU capacity, or other shared resources are needed. And these things are interesting things to exercise. A lot of this can be done pairing with programmers in the IDE and using mocking to help simulate these conditions. But you're asking the question, what if this breaks? These are not things that are defined in the API. These are not things that are defined in the requirements. These are harsh constraints. These are stressful things. So we're basically doing stress testing in some ways here, trying the application in a harshly constrained environment. And there's, of course, mechanisms to do this. There's a whole slew of software attacks as published by James Whitaker and Doug Hagar, John Hagar, sorry. These are great ways to try to find a weakness in software by using deliberate attacks of it, and they're all cataloged. Whitaker's book, How to Break Software, defines about 90 different attacks, beautifully described. So you'll see he wrote 3 books: How to Break Software, How to Break Web Software, How to Break Software Security, and let's see, the other one is How to Break Mobile and Embedded Software by John Hagar, I believe, is the 4th one. How to Break Software. Fantastic testing for robustness. Is the application actually robust? Is it solid? Then we have non-functional characteristics of a system, and there is a huge number of non-functional attributes of a system that might have an impact. You should consider ones that matter. Not all of them matter. These are often called the ilities: usability, reliability, availability, scalability, maintainability, and also performance, security, privacy, as well as power consumption and stuff like that. These are all important non-functional attributes of a system. And you should work with your team to try to find out which attributes matter and then figure out ways to exercise these. And this requires a type of testing that's more or less like an experiment. It's like a science or a physics experiment where you basically will take the system and set up a precondition, modify some factors, observe the results, and see if it's within some sort of valid range. So it's not like a test that just passes or fails. It's a test that has a lot of things you want to study. So this is quality factors or attributes of a system. Of course, there's usage scenarios. How is the system used? And if you have a whole slew of APIs available to you, well, the question to ask is, what are the different pathways through these? What are normal paths? What are alternate paths? What are error paths? What are the ways people can sequence through the microservices to get their job done? So those are usage scenarios. So we want to know who's the user and how they're going to use the system. What type of programs are we going to write with the system? What other things do people do at the same time? We have end-to-end testing becomes important, really important for microservices, where we want to make a chain of calls of services for every possible step we're going in. And this might include program things and manual things, and all sorts of stuff that might be involved in it. Third-party stuff, external stuff, firewalls, all of these type of things. And basically, usually you'll be able to draw some sort of flow chart or control flow diagram to describe the workflow of your system, and then try to find interesting paths through that workflow. So that lends us to the subject of exploring paths. Think of the map of London. How do you get from point A to point B? And it looks like if you follow the maze and it allows looping, that there's an infinite number of paths. But if you have a lot of possible pathways through your system, you can study those paths and try to find a subset of those paths that will reasonably exercise the system with a small number of tests, or a reasonable number of tests. And the type of analysis for doing this was popularized, I guess, by a guy called McCabe. It's often called cyclomatic complexity analysis, and it's common in white box testing done when people design unit tests. But it applies to anything that's a flow. So if you call microservices in different orders to achieve different results, that's flows, that's pathways through a system. You want to exercise different types of path, and it's almost impossible in complex systems to exercise all the paths. So we want to find a meaningful subset of those paths. And then there's white box approaches. This is where you actually, work with the programmer, look at the code, figure out what the risks are based on what's changed in the code, and exercise around that. We mentioned stress testing to assess the robustness of the software. Many of my customers will actually fail services. They will fail, or will crash their server, reboot the server, and see if the application picks up where it left off. This is very interesting resilience you get for robustness. The type of testing people do there is sometimes called chaos monkeys, where you basically crash servers in the background. We can do corruption of data. This is fuzzing data, they call it, randomly corrupting data, and looking at how the system behaves. Hopefully, the system notices that the data is corrupted and gives you an appropriate error response before it processes it. So we get to, those are sort of the types of focuses of REST API risks and what we can look at in testing. There's also some elements of test design that are critical for REST API system. And I mentioned earlier that we're looking at payloads with a lot of variables. It's very important to identify what are the variables that influence or are influenced by the software that we're testing, the service that we're testing. Some of them will be explicitly defined in the payload, but not all of them. You've got to look at what the system is doing broadly and talk to your programmers to figure out what factors, what conditions influence or can influence or is influenced by the behavior system. Anything that changes can be considered a variable. It doesn't necessarily have to be in your payload, although the payload is a darn good place to start. It's a darn good place to start to find values, to find variables. This is just an example of the type of variables that you might see if you're looking at testing the API for Gmail, for example. So if you look at, there's variables related to the login, the state of the inbox, the structure of the email, the environment that things are running on. But there's also variables related to, because it's in the world of Google, search results, time synchronization stuff, GUI stuff. I always love to try to send an email and receive it before I sent it by changing time zones. Tricky stuff like that are interesting risks associated with email synchronization. When you look at variables, once you've identified variables that are relevant and in scope, you can classify them. Some of them could be considered mandatory variables. They must be there. They must have a value. Some are optional. They don't have to be there. Some are conditional. They sometimes have to be there, but not always. And there's, of course, a bunch of implied variables which don't really get written down explicitly, but do have an influence. For example, how many records are in your database is not a parameter that you send in a payload, but it influences the behavior of your system if you're searching the database. So that's a variable. Now, the beautiful thing about variables is once you've sort of identified them, and I like to sort of visualize them like in a mind map, but there's only 4 things that I can do with a variable once I've found it. If I'm going to be testing, and this is a very critical test design decision, I can ignore a variable, just deliberately ignore it. I will not check this. If we find a bug related to it, it'll be by coincidence. I'm not looking at that. I'm not exercising that variable. I'm going to ignore it. Then there's default variable values. So some people will choose for variables a default. It's not that we're ignoring the variable, but we're not going to be manipulating it. So we're going to set it to some predefined default value. That's very handy for security parameters, for example. And then, of course, we might choose specific values to exercise the behavior of the system. And other variables will observe. So some, of course, you can combine observing with setting variables at the same time. So one example of a variable that I would observe is the percent CPU saturation on your processor. That's not a variable I would set, but it's a variable I would observe. And then the types of data, these are standard types from a JSON object, strings, text, strings, sequence of text, whole numbers, that's integers, which could be positive or negative, Boolean, which are true or false, right? Objects and arrays are collections of things. So objects are key value pairs, and then an array is a list of them, or a list of things. When we do a domain analysis testing, for every variable, we're going to look for classes, partition them. I like to suggest that we should look for these classes by taking a look at the application logic, input method, or how things are stored or processed in memory, And this memory thing comes usually from the programming environment. You'll find out what the maximum and minimum values for each type is. Input method is usually for an API parameters that are strings that are passed around, and A stuff comes from the definition of the business logic. So that's application logic. And I just try to map these out. And once I've got a map of these things, the end node is where I'd be testing. I'd test at least one member of each of the end nodes of an equivalence partition. So that's a type of test design. Anytime you have variables with ranges of values, it's handy. Boundary values, boundary bugs exist all over the place. We've been trying to get rid of them since I started programming, and they're still there. It's probably because they're more perception than they are clarity of requirements. But I would suggest that anytime you have variables with classes with ranges, exercise the extremes. Exercise the extreme. And then when you have a complex workflow in your system, try to find a reasonable subset of the pathways through it to exercise. So you may have a system that has, hundreds of millions of possible pathways through it, and you only have the energy or time, reasonable time, to test like 20 or 30. Well, how do you find those 20 or 30 paths that will help you learn the most about the system with the least amount of tests? And one way to do it is called control flow testing. And this I found invaluable for microservice architectures. In control flow testing, we start by drawing a picture called a control flow diagram. And then from that diagram, we apply an algorithm to find what are called the basis paths. And the basis paths would give us the minimal set of transactions where you would exercise each step in the whole workflow at least once, and every outcome from every decision, every way it can go at least once. And you can create any path through the system by combining the basis paths. So the basis paths start with these control flow diagrams. Circles represent the steps or the calls. Edges are the order of operation. You can compute the number of basis paths with McCabe's calculation here. E is the number of edges, N is the number of nodes, E minus N plus 2 is the number of paths, so that's just to give you the number of paths. And to find the paths, there's some algorithms that are published in many different places. McCabe has published them, but Lee Copeland, in his book A Practitioner's Guide to Test Design, has published them. And I have also got a tool that's available if you'd like it, called the Paths tool, PATHS, which, if you're interested in getting a copy of it, you can just email me or send me a note, and I will be sure to get you a copy of the tool. It's built by some McGill students. It's not the most robust product in the world, but it helps you quickly identify the basis paths. Take a look at this example. This is a workflow of a service architecture that was implemented at one of my customers. We take that workflow, draw it as a control flow diagram with the circles and arrows. We compute the number of basis paths. It works out to be 22. And by applying the algorithm in Lee Copeland's book, A Practitioner's Guide to Test Design, we identify these 22 paths. By testing these 22 paths, we were able to find a lot of cross-feature interference bugs in the system, and my customer was able to implement these, set up the transaction data, run the transaction, find great bugs. After the bugs were fixed and they could regress with these without failure, they were able to deploy to production with no further software engineering work required. It's an amazing subset of all the paths that will very thoroughly exercise your system. That's called the basis paths from control flow testing. You can also study, if you have historic data, Pareto combinations. That's take a log file of your transactions, sort it by frequency, and you'll find that 20% of the transactions happen about 80% of the time in a lot of computer systems, and that sweet spot is called your Pareto sweet spot. So by testing those, you will basically build regression confidence. You're not going to find a lot of outlier bugs, but you're going to make sure that the most common paths work reasonably well. Another type of analysis you might do is failure mode analysis. If you've got all the services mapped out, you might try to identify which ones are critical, and you list that with all your usage scenarios. So the rows are usage scenarios, The columns are the process elements or the microservices, and what happens if they fail. And this analysis basically helps you identify which services um, impact which scenarios. So you can say, let's simulate this failure while we're doing the scenario to see what happens, then correct it and see if you recover correctly from it. That's called failure mode analysis. Thank you very, very much. Have a good day.